Hello. In the previous lecture, we normalized the Navier-Stokes equation using the scales that we have talked about, velocity, length, and time scales. And that produced for us a Reynolds number, a dimensionless number, that was the ratio or that incorporated viscosity, density, length scale, and velocity scale. And we started looking at what that Reynolds number might mean. In one arrangement, we thought of the Reynolds number as a length scale ratio of an inertial scale to a viscous length scale. And in another arrangement, we thought of it as a velocity, inertial velocity to a viscous velocity, just because it has a viscosity in there. And there was a typo in the previous lecture. We could think about it as a ratio of time scales, and it would be the viscous time scale over the inertial time scale, not the inverse as we had in the previous lecture, so please correct that. And now let's look at what those scales mean. And let's look at the inertial scales. So take a ball in flight. The ball has a dimension length scale L, which makes sense for it to be the diameter of the ball. And the ball is traveling to the left at a velocity u, so the air that we're considering is moving to the right at the same relative velocity. So it's the velocity seen, so what we're drawing here is the velocity seen by someone sitting on the ball. And then we can, from those two, we can produce an inertial time scale, L over U. So that would be the time for the ball to move or clear this distance and occupy this new space. So the inertial scales are easily understandable. We can make sense of them. The U, the L, and the inertial time scale L over U. But what do the viscous length scale, time scale, and velocity scale mean? So we know from just by looking at the units that they have viscosity in them, and that's why we call them a viscous time scale. But what does that actually physically mean? So one way of thinking about this is, let's look at this ball as it travels through the air, or you can look at the air particles as they come past the ball. So the no-slip condition requires that the fluid particle, the air particle that's sitting on the ball, will have the same velocity as the ball. So in this case, if I have my ball stationary and the air is coming from left to right, this fluid element will have zero velocity. And the effect of the ball on the velocity of the air will start right here, right towards the leading edge. That's the first part of the ball, or that the air sees. And so the no-slip condition, so this fluid particle has become stagnant because it has the same velocity as the ball, and that no-slip starts propagating away from the ball in this direction, so normal to the direction of the ball. And this is the region of effect of the no-slip condition is almost zero towards the left part of the ball, what we call the leading edge. And as you move further downstream, that effect starts growing larger and larger. And so the time it takes for the ball effect on the air to propagate in this direction is what we call the time scale, the viscous time scale, because that's due to viscosity, the stickiness of the air particle to the ball. And then it makes sense that, so that is a time scale, the time it takes, a viscous time scale, the time it takes for the stickiness effect to propagate from the surface of the ball into the air that is undisturbed outside from the ball. And then we now can think about a length scale. So what is this dimension, which we call delta? So this thickness, if we call it delta. So that would be our viscous length scale. And then how fast does this effect propagate from the surface of the ball into the undisturbed air away from the ball is the viscous velocity, because it's due to the viscous effect. And now here is a another example that I would like you to look at and actually to try and do at home. So go to your kitchen, get a raw egg, actually get 2 eggs. Boil one in water so it becomes hard boiled, and then place the 2 on a table. And now give each one a spin, an equal amount of spin. And you'll notice that the hard-boiled egg, once you give it a spin, it's going to remain spinning for many more seconds after you take your hand off. So you take the egg, put it on the surface of a table, and then just give it a spin. So a hard-boiled egg will actually spin around this axis a number of spins. It'll do maybe 3, 4, 5, 6 spins. But if you look at the raw egg, you give it a spin, and once you lift your fingers off the egg, it's going to almost stop. And I would like you to think about that in terms of these scales and how viscosity is involved in that. So that would be in one of our assessment experiments that we want to do at home. So please take your time to look at this and think about it, and try and contrast and compare to the ball that's over here. This region where we have the effect of the nose slip traveling in a direction perpendicular to the ball, we call it the boundary layer. And this delta would be the boundary layer thickness. So let's look at this in a little bit more detail. If I were to make the air visible, if I were to visualize it, if I can invent a tool to let me see what the air is doing, then I should be able to discover this effect. And in fact, you can do that now in today's wind tunnels. So here is a football, and as you can see, the airstream is coming from left to right, and the ball is kept stationary in a wind tunnel. And what you'll notice is that the effect of viscosity, it's very easily seen in the region behind the ball, which we call the wake. And depending on the Reynolds number, which is defined as here, that the size of this wake can be different, and the behavior of this wake and the nature of this wake can be different for different values of Reynolds number, primarily because the relative sizes of this viscous length scale to the inertial length scale will become different, just because that's the definition of the Reynolds number. So that's what I would like you. So that's one of the physical meanings of the scale ratios, and then you can extrapolate to time and velocity scales. The more famous or the more advertised meaning of the Reynolds number is that it is a ratio between the inertial fluid forces to the viscous fluid forces. So let's work backwards, and let's take that this is being the definition of Reynolds number, or the meaning of Reynolds number. It's the inertial forces to the viscous forces. And let's see if we can recover the Reynolds number. So inertia is mass times acceleration. Inertial forces is the mass times acceleration, while a viscous force is just the shear stress times the area. So that's what we have here. And what is mass? So let's do them in the using the scales, the velocity scale, length scale, and time scale, which is L over U. So let's plug those in. So a mass is a density times a length scale cubed, density times volume, while acceleration is just a velocity squared divided by L. So density times L cubed, velocity squared divided by L. And the shear stress is tau, and it's the viscosity multiplied by du dy times an area which scales with L squared. And let's plug in for tau. So tau is the viscosity times the velocity U scales with the velocity scale, and y scales with the length scale L. So we'll plug U over L, and then we have L squared. So if we look at this now, let's try to clean it up. We get rho L square U square, and then I get UL at the bottom. So the UL goes with each of the squares, and I actually end up with having the Reynolds number that we're familiar with. So in fact, the Reynolds number is a force ratio. It's a measure of the effect of inertia to viscosity. So when Reynolds number is 0, that means the viscous forces are very large compared to inertia. So inertia becomes negligible, and that's what we have seen in the previous lecture. While when you go to an infinite Reynolds number, that means the viscous forces are negligible, and the inertia is the dominant force in the flow. Just like what we mean by dominant is we can explain it by going to the example of the ant and the elephant. The reason why we see an ant, we can easily imagine an ant walking on the ceiling, while we cannot really imagine that for an elephant, is because the dominant force in an elephant is its weight, its gravity, while it's not that dominant in the case of an ant. So an ant can defy the effect of gravity. Very good. So let's just recap for a second how we got to this point. Well, we started by the definition of scales, length, time, and velocity scales. Then we brought those we infused them into the Navier-Stokes equation. And after cleaning the Navier-Stokes equation, we ended up with a dimensionless number called the Reynolds number. And we just now and in the previous lecture described what happens in the limits of Reynolds number going to infinity or going to 0. And what it means, what is the meaning of Reynolds number being the effect of viscosity to inertia. So there are, if you look at other fluid equations, so there are so many other fluid equations that deal with compressible flows, equations that deal with surface flows, and so on and so forth. You can non-dimensionalize each one of those equations, and each one of them is going to give you a dimensionless number. So in fact, in fluid mechanics, we have a lot of many other dimensionless numbers, and we will cover some of them in this lecture. And you want to think about them the same way as we thought about. You want to think about them and how we obtain them the same way as you think about the Reynolds number and what it means. It's a ratio of two effects. So let's look at some of those effects. So if you look at and where we see them, so we see Reynolds number in almost every type of flow. The number we're going to look at in this chapter is Mach number, is one of the numbers we want to study, and we have seen that in the previous chapter when we were discussing continuity, the continuity equation, and we see it when we're talking about the density of the flow being constant or non-constant. So when it is not constant, that means the flow is compressible, and we discussed previously what this actually means and how that is related to the Mach number. So the Mach number being the velocity of the flow divided by the sound speed. One dimensionless number that we want to look at in your take-home experiment is the Froude number, and as you can see, it has inertia in it, inertial effect, and then you have a gravitational effect because it has a G in there. And this you can see in ocean-going vessels, in ships, in rivers. These are all the behavior of these systems, and these flows depend on the value of the Froude number, whether it is very large, very small, or somewhere in between. There are many other numbers that you will see in other courses, like heat transfer, or so you'll see some of those in your heat transfer course, your Grashof and Rayleigh number, as well as Prandtl and so on. But for fluid mechanics, we're going to stick with the one with the highlighted numbers: Reynolds number, Mach number, Froude, for our experiment, as well as Strouhal number. We will talk about that in a second. And it's got to do with we will see it in flows that oscillate. So, for instance, you're breathing right now. So you have air coming into your lung and leaving, and it goes in an oscillatory fashion. If you see a bird flying, it will be moving at a forward speed, while at the same time its wings are flapping at a certain frequency. So the Strouhal number is an oscillatory effect relative to an inertial effect. And then we will consider roughness effects. So that will become useful in when we study pipe flow examples or pipe flow problems. And then in aerodynamics, we will be looking at lift and drag coefficients, as well as shear stress coefficient, or what we call the skin friction coefficient. And maybe we'll look at the surface pressure coefficient. In fact, we will talk about that in a few minutes, the surface pressure coefficient and the wall shear stress coefficient, the skin friction coefficient, as they relate to the lift and drag, and as we have discussed them when we were talking about the cruising aircraft example, when classes have been held at the university. Okay, so there are many dimensionless numbers, but we will only be focusing on those numbers. And now we know, just by looking at the Reynolds number and how it came, that there's a way to derive these numbers, and they show up, and they have a physical meaning to them. Right, so Reynolds number. So let's talk in detail about some of those effects. Reynolds number, we'll see it in many types of flows, as we have just discussed a minute ago. Mach number, we see it in compressible flows, and we discussed when we were talking about the continuity equation why the speed of sound is important, because it's the speed at which information travels in a fluid. That's how fast information travels. And because it's physically possible for you to move an object faster than the information travels, and in that case you start forming shocks. And shocks cause density variations, and hence our flow becomes compressible or incompressible. So the speed of sound, we came across this for ideal gases. It's the specific heat ratio, Cp over Cv. And R is the universal gas constant, and T is the temperature. You plug in numbers for air, and you'll see that at sea level, your speed of sound is between 340 and 350 meters per second. And this is a nice formula because you can use it for any type of ideal gas. For liquids and solids, there isn't a formula as predictive as the one that we have for ideal gas. So we have to measure it experimentally. And the fluid that we are most interested in is water, and the speed of sound in water is about 5 times the speed of sound, maybe 4 to 5 times the speed of sound in air. So it travels much, much faster. And in metals, it's maybe 2 to 3 times faster than it travels in water. Now I would like to show you a video that explains the Strouhal number. Okay, so let's consider, we're talking about a Strouhal number, so let's consider this cylinder, or actually this football, that is traveling to the left, and hence air is coming from the left to the right. So here we're keeping this football stationary and air is going past it. So as we have seen in a previous example, we get a wake behind the football, this sphere or even a cylinder, and that wake has some oscillatory behavior that becomes more manifest as we go further and further downstream. So let's look at it. Let's play this video and see how the flow oscillations occur. So you'll see the boundary layer from the top peels first, so it's mostly blue and then it's mostly red, blue and then red, because of the alternate shedding of the viscous effect from the top and the bottom of the cylinder. So this is one example of the shedding of vortices. Now, the reason why so in this particular example, we're holding the football fixed in space, primarily just like holding it on a stick and in a wind tunnel, so the ball is not going anywhere. But now, what if we allow that ball to move? So we will see. Now we can see the effect of the vortex shedding on the ball itself. So here we have designed this video or this setup so that the ball does not move by the pressure fluctuations between the top and bottom sides of the ball. So let's look at a different example here, and let's look at this guy. So here you have a cylinder, you have an airstream by this fan, and as the airstream hits the cylinder, it's going to create a wake, and it's going to create those shedding vortices, the red and blue ones that in the previous video that showed the direction of rotation of the flow. But now we allow the ball or this cylinder to move along those in the vertical direction. So let's see what happens. So you'll see, depending on the Reynolds number, the oscillations, the oscillatory motion, the frequency at which the cylinder oscillates up and down can vary. Also depending on the speed at which this the fan is blowing and the diameter of the cylinder. So that's an oscillatory type of motion that is of interest to us. Okay. So we have seen in these examples the what we mean by an oscillatory type of flow motion, and we saw it in the vortex shedding, and also we saw it in the motion of the cylinder as it was allowed to oscillate in one direction under the effect of the shedding vortices. So this effect, so the Strouhal number is a flow, you could think of it as a flow time scale divided by an oscillatory time scale. So U over L is the flow time scale, while the oscillatory time scale is the omega, is the frequency. So it has units of 1 over time. Or you can think of it as a frequency, an oscillatory frequency divided by, so oscillatory frequency divided by a flow frequency, which you get from dividing the velocity scale over the length scale. Now, this oscillatory behavior of fluids has been designed by some companies into a flow meter. So if you have a pipe right here of diameter d, you can buy this piece and stick it to the pipe. It's a pipe fitting, and what it is, it actually measures the flow rate, and the essential piece of it is an object just like the cylinder. Here it has been engineered to give you a shedding process, a vortex shedding process of positively and negatively rotating vortices that is consistent. So these vortices, as they come past this strain gauge, they will induce positive and negative pressures and strains. And when that happens, that strain sensor is going to give you, as a function of time, is going to give you a signal that looks like this. So this is the strain gauge signal, and that signal has a frequency, and that frequency is associated with the shedding vortices. So we can measure the frequency of these vortices shedding by the strain sensor, and then that frequency, if we know something about the Strouhal number, if I measure the frequency, I know the Strouhal number, and I know the diameter of the pipe, then I can get the flow velocity. And if I know the diameter, I can get a flow rate. So this is a vortex, what we call a vortex flow meter. It's based on this oscillatory behavior of fluids. So you see now we're talking about actual real-life fluid mechanics that you can actually take to the bank, go use it in your various engineering problems. And now if we look at, so this was our cylinder in the simulation video, and the reason why that cylinder did not move is because we held it. So the holding force that we had to counteract the cylinder being carried away with the flow is what we call the drag force. And the force perpendicular to the to the direction of the flow is what we call the lift force, just like we have seen before. So we have lift and drag, and that happens in any type of object moving in a fluid. So you have a fluid moving at a velocity v, and you have an object, and you will get two bulk forces of a lift and drag forces, and defined as so. The lift force has a 90-degree with the direction of motion, while the drag force is in the same direction of motion of the object, but in the same direction of motion of the fluid on the object. So that's the drag force. And the reason why we have lift and drag force on objects is because we have pressure distribution and shear stress distribution. And this is where, so we have those four quantities: lift force, drag force, pressure, and shear. And these we have dimensionless numbers that are used very much in aerodynamics, in the study of fluid flows past objects. So the lift coefficient is just a dimensionless lift force, with the non-dimensionalizing being the dynamic head, rho u squared, and some area defined for the specific problem. Drag coefficient, it's a dimensionless drag force. And then we have, as we have seen before, the pressure coefficient and the skin friction shear stress coefficient, the CF, and that's your pressure or surface pressure coefficient. And for these objects, you have a surface that has a roughness, height, epsilon, and that sometimes can play a role. It can affect the lift, it can affect the drag, the skin friction on your object, even the pressure coefficient too. It can affect it, how rough the surface is. So we just saw the two videos on the cylinder that was in cross flow, where we saw the movie for the shedding vortices, and then we had deduced that there was a force on the cylinder that prevented it from moving, and that's what we call the drag force. And when we removed some of the restrictions on the motion of the cylinder, we were able to reveal the lift force on that cylinder. It's the force perpendicular to the flow direction. So now let's look at some experimental data. So here is an empirical figure. It plots the Reynolds number against the drag coefficient, and by empirical, it means this is an experiment. This is a figure that has been obtained from experiments. The drag coefficient defined as the non-dimensional drag force, while the Reynolds number as we have defined it before. And we have two plots here. One, the drag force on a cylinder, and the other is for a sphere, so such as a football. And you'll see the trends are very similar for the two. So let's look at the trends. At very low Reynolds number, we expect, so Reynolds number very low means that your viscosity is high, the effect of viscosity is high, so the non-dimensional drag is actually very high. So at low Reynolds number, the non-dimensional value of drag, CD, is extremely large, and you can see it goes, this is a logarithmic scale, and it increases very log linear scale, and it increases extremely fast. Now, as our Reynolds number increases, the drag force, the non-dimensional drag force, drops very fast until we get to a Reynolds number of almost 1,000. That drag force now, the non-dimensional drag force, becomes almost constant for a cylinder of maybe 1.2 here. For a sphere, it's pretty much around 0.5, and it stays constant, and what we call it to be independent of Reynolds number over this region, all the way up to maybe between 200,000 to 500,000. And after that, there is a very funny phenomena that happens where the drag coefficient drops dramatically from a value of 1.2 by a factor of 6 times to almost 0.2. And that's called the drag crisis on a cylinder. But of interest to us is this particular region where the Reynolds number is almost, the variation of Reynolds number do not affect the variation in drag. But we see as our Reynolds number is very small, the drag coefficient is very highly dependent. The drag coefficient drops very fast at low Reynolds number, because if you go to the non-dimensionalization of the Navier-Stokes equation, here we had creeping flow where the effect of viscosity is very high, and as your Reynolds number gets higher and higher, the effect of viscosity is negligible, and then it's only inertia dominated. And somewhere in between, we transition between those two. And this is how we can get the drag force. If we know what Reynolds number we are at, we should be able to get the drag coefficient. And once you get the drag coefficient, you can get the drag force by knowing the dimensions of the flow, the length scale, velocity scale, and the time scale. And same thing for the Strouhal number. Let's look at what the Strouhal number behavior looks like as a function of Reynolds number for the flow behind a cylinder. So think about that video where we had our cylinder where it was allowed to move in one direction under the effect of the flow. So here is what you here's the Strouhal number effect. So we have plotted the Reynolds number on one axis, and then here we have plotted the Strouhal number. So for very low Reynolds number below 100, the effect of Reynolds number on the Strouhal number is actually very significant. So Strouhal number goes from almost 0.5 to almost 0.2 at a Reynolds number of 100. So it increases by a factor of 4. But now let's see what happens between, and these bars, the vertical bars, represent the uncertainty in the measurement, or in some other sense, it's the fluctuations, because this plot wasn't generated by a single experiment. It has been generated by many experiments by many people all over the world, and that's what makes, and each one of them has used a different value for density, for viscosity, for diameter, and they were still able to collect all that data and plot it on a single plot. So that's one of the powers of working with dimensionless numbers, such as the Strouhal and Reynolds number. But you see, once you get to a Reynolds number of 100, so large enough Reynolds number, 100 is pretty much 2 orders of magnitude larger than 1. So the effect of inertia is much larger than viscosity. The Strouhal number becomes almost constant, of almost 0.2, and it doesn't vary much. All this happens all the way from a value of 100 Reynolds number to almost maybe 300,000, 200,000 over here. So the conclusion of this plot is that once you're beyond the viscous region, the viscous effect, once your Reynolds number is high enough, above 100 or 1,000, your Strouhal number, the oscillations of these vortices, the frequency, the non-dimensional frequency becomes constant. And for us, this non-dimensional frequency is 0.2. So now you can actually take this picture to the bank and you can use it in your engineering problems if you want to evaluate at which frequency your object oscillates. If any of you plays any of the wind instruments, you blow into the mouthpiece of the instrument, and what happens is there is a blade, or there's a sharp edge, and as you're blowing on that flute, you're going to get a vortex shedding process going. So at one instant the flow will be going above the sharp edge, and at another instant below, and this repeats 300 times per second, or 400 times, maybe 440 times per second. That gives you a note of A, and so on and so forth. So the frequency at which the shedding of these vortices is the audible sound that you hear. You hear 440 hertz. That's the note of A, and so on. And if you want to get to a B, so that's a slightly higher note, you can increase your wind speed, or you can change the angle at which you blow, so you hit a sharper part of the edge, which means you're getting to a you're playing with this diameter D, and that gets you Strouhal number being fixed or being known. That gives you, by playing with the velocity, that gives you a different frequency. So this is a basis for pretty much wind musical instruments. So now when you think about wind instrument music, you want to think about Strouhal number in there, because there is there's the velocity scale, length scale, and from those two we get a frequency, which is the frequency that we hear, the oscillatory frequency. So we talked about lift, drag, Reynolds number. Last thing we want to talk about is the roughness effects. So that we'd expect that if I have my cylinder to be rough or smooth, that will affect the amount of frictional force, the drag force on my cylinder. And here we have plotted the drag force, non-dimensional drag force, versus the Reynolds number for a number of cylinders. One of them has a smooth surface, and as we increase the surface roughness, so that's the epsilon, is the surface roughness, non-dimensionalized by the diameter of the cylinder. So on this plot we have three dimensionless numbers: Reynolds number, drag coefficient, and the roughness factor, the epsilon over d. And we can see what effect that has on our cylinder. Then we're in this slide we're talking about the drag coefficient and the lift coefficient. So if you have, stick your hand out of the window of a moving car, watch the moving cars though, and depending on how you angulate your hand relative, or the palm of your hand relative to the airstream, you can get a positive force that pushes you upward, which we call a lift force. It can push you upward, and if you have a negative angle alpha, that will push you down. So that's your lift force, and it's the force perpendicular to the velocity u, just like we have spoke before. And at the same time, you're going to get a force that pulls you back, which is the drag coefficient. And now we have talked about the drag coefficient for a cylinder, but here, this section right here, this object, we call the an airfoil section. So if you, and I believe we talked about this in chapter 3, if you take the wing of an airplane and you get a saw and you try and cut through it, you will expose this cross section, which we call the airfoil section. And for that airfoil section is associated with a lift coefficient plot versus the angle of attack. So the angle of attack, because it's a ratio of two lengths, it's a dimensionless number, and the lift coefficient is also a dimensionless number. So we can conclude from these plots that we have looked at so far is that the non-dimensional, we've always plotted one non-dimensional number against another non-dimensional number, and maybe we have multiple curves for maybe a roughness effect or some other factor. So dimensionless number help us describe flows better, and I think the power of it is that it generalizes our results and extends it to experiments well beyond the ones that we have particularly done, because we could be looking, because if the alpha is 20 degrees or whatever degree, it's the tan inverse of length 1 over length 2. That length 1 over length 2 could be 5 centimeter to 1 centimeter, or it could be 5 meters to 1 meter. So the difference in scales is huge, but the dimensionless number is still the same for both cases. And even though the lift force in the small case, the 1 centimeter case, can be maybe, the lift force could be 1 Newton. In the case that is 1 meter or 5 meters, the lift force, instead of being 1 Newton, it could be 100 kilonewtons or so, depending on the problem parameters. But still, those two problems, as long as I get the same section, I'd expect that I will get the same dimensionless lift force with the angle of attack. So it's a very powerful tool, that business of using dimensionless numbers to describe experimental data. And by the way, this figure comes from experimentation, which, if you take the aerodynamics course, we will discuss it in a lot more detail. And our plan for the next lecture is to solve some problems. So I will talk to you next lecture. Thank you.